Test 1, 2, 3.
Hello, hello. We all good?
Yes, we are. Hi, John. Hello, everyone. My name is Anna from APNIC, and I will be your MC for this session. This is the last day of the conference and also our last technical session. I hope we are learning and enjoying this space where we can virtually interact with our friends from the community. So we want to hear your questions or your comments during the session. If you want to ask a question or write a comment, you can either use the raise hand function in Zoom and you will join the queue for voice question, or use the Q&A button in Zoom for text. And I will read your question or comment to the speaker. I'd like to remind you to be mindful of the code of conduct, which is published at the conference website and in the chat box. And since today is the last day, we would like to see your selfies while attending the event. So why not post them on Twitter or Facebook using the hashtag APNIC50. I am now inviting Shaila Sharmin from Brack Bank Limited, who will be moderating this session. So over to you, Shaila.
Thank you, Anna. Can you hear me?
Yes, we can, Shaila.
Okay. Hello, everyone. Good morning. Welcome to you all in the technical session 5 of APNIC 50 virtual event. I'm Shaila Sharmin from Bangladesh and program committee member of APNIC 50, who will be moderating this session. And I would like to invite our first speaker of this session, Jonathan Brewer. He's consulting engineer and also working with NSRC as a trainer and network engineer. He will be speaking on microwave and MM wave wireless backhaul network. Over to you, John, for next 30 minutes. Please feel free to start.
Hello, can you hear me?
Yes, we can, John.
Yes, we can.
Fantastic. Okay, so I'm John Brewer, and you may know me from my work with ISPs in New Zealand, or maybe talks at APNIC on satellite or submarine cables or networking in the Pacific Islands. I started working for an ISP in Kansas 25 years ago in 1995, so I've been doing this for a little while. I eventually got tired of being constrained by cables, and around 17 years ago, when I moved to New Zealand, I started seriously working with wireless. So I took this photo on the 47th floor of Auckland Sky Tower, where many of New Zealand's telcos and ISPs have microwave and millimeter wave equipment. I've been working in this building on and off for 15 years now, and I'd say it's my favorite building in Auckland. Great views, eh? So this isn't me on the tower, but this is one of my antennas. Yes, this little tiny one amongst all of the giants. This photo was taken in 2006, and the antenna was providing the primary link to the internet for an ISP called WiseNet in rural New Zealand. It ran at 10 megabits per second full duplex. That was the whole ISP running at 10 meg. Since this link, I've designed at least 1,000 more point-to-point microwave links, some of them operating 500 times faster. So what do we mean by microwave and millimeter wave and millimeter wave spectrum? It's these frequencies here between 5 and 30 gigahertz that are called microwave, and above 30 gigahertz that are called millimeter wave. Sometimes in marketing and popular material, the 26 gigahertz band is also called millimeter wave. So this chart shows the general availability of microwave and millimeter wave spectrum available for point-to-point linking in the APNIC region. You usually need a license from your country's government to operate a service in one of the blue bands, and you usually don't need a license to operate one in the green band. The green bands are what's called ISM, or Industrial, Scientific, and Medical bands, which are a class of radio spectrum and a class of devices using that spectrum, a few globally coordinated spectrum bands that are generally free for anyone to use. So we'll look at the extent of these bands and the licensed bands and the ISM bands and their availability across a few APNIC countries in the next slide. So this is the availability of the spectrum by band in some countries in the APNIC region. I found this detail by analyzing the national frequency allocation tables for each country in the region that I could find. If your country isn't here, it means I couldn't find the detail, and so maybe you could help me find the information after the talk. If you don't know me already, my contact details are in the last slide. Just get in touch. So I've gone through the most common microwave bands available in the region, and I've estimated the total capacity of a single license on a single polarization in each band, and the total capacity of each band, assuming ideal conditions. We'll get to talking more about those ideal conditions a bit later in the talk. In general, the most you can practically get out of a frequency band below 10 gigahertz these days is 500 megabits per second per channel and polarization. And most of the bands only have a few gigabits of capacity available on a single path before you run out of radio spectrum. Moving into the middle bands, you see a bit more capacity. The 18 gigahertz band is the lowest frequency band in most markets where it's possible to get a full gigabit per second link on a single channel, a single polarization, and a single license. So notice here the 11 gigahertz band has more available spectrum than any of the other bands in this range, and twice as much as any spectrum band below 10 gigahertz. So we'll see more of the 11 gigahertz band and its popularity a bit later in the talk. Once we get up to above 20 gigahertz, there's just heaps of capacity. We all good here? If you license channels in either of the 23 or 37 gigahertz, you could get more than 20 gigabits per second of capacity across a single path. So you can get 1 gig in a single carrier at 23 gigahertz. And if you licensed all of them from one point to another, you could get 20 gigabits of 22 0.96 gigabits of radio capacity from one point to another. Now that used to seem like a lot of capacity, but with fiber these days, maybe it's not. I know Shaila in Bangladesh, people have been using 100 gigabit switches for a couple of years now. So we all need lots of capacity. Moving up in the spectrum, there's basically nothing going on at 50 gigahertz, but in the 60 gigahertz ISM band, it's possible to get a couple of gigabits per second of traffic through a link. And there's a lot of radio spectrum to go around. And if you remember our chart from a few slides ago, in most markets, that band is free to use. It does have some technical caveats though, as we'll see soon. Finally, we get up to the 80 gigahertz band, and it's the first time we see the potential for an individual microwave link to run at 10 gigabits per second. That's right, you can get a radio link to go at 10 gigabits per second on a single channel. And you can buy equipment today with 4-channel microwave links that runs at 40 gigabits per second. The 80 gigahertz band has some serious capacity. Looking at all this together, I've made a chart showing the relative amount of capacity per band in the generally available bands in the Asia Pacific region. I keep saying generally available because there are a few small bands that are available in some countries kind of randomly, but I've considered the ones that are mostly available in most countries. Anyway, look again at how much spectrum we've got in the 80 gigahertz band compared to all of the rest of the frequency bands. So 80 gigahertz has just huge capacity. Let's only use 80 gigahertz. This is a valid point, right? I installed New Zealand's first and second 80 gigahertz links in 2007 and 2008, mainly because of their massive capacities. Back then, it was the only equipment you could use and get a gigabit per second of capacity on microwave. So you'd think everybody would be doing 80 gigahertz by now. It's 2020 already. And yet, here's a distribution of licenses across the various microwave and millimeter wave bands in New Zealand, with the height of the bars proportional to the number of licenses issued. You'll note on the green bars, there's 0. The ISM bands don't require licenses, so I don't know how many links have been installed there. So what's popular for microwave in New Zealand? Well, the 11 gigahertz band is the most popular. 7, 13, 23, and 18 round out the top 5. There's not a lot going on in the 37 gigahertz band, and 80 gigahertz band is actually in last place in terms of number of licenses. It's got the most capacity and the least amount of licenses. Why are we so heavy on low frequency licenses given the high capacity of the higher bands? So in this next part of the talk, I'll discuss a few properties of radio spectrum bands that have led to some of the bands being more popular than others. Here we've got a pair of constellation diagrams showing the lowest and highest modulation methods of modern microwave equipment. One thing to note on the bitrate side, each doubling of complexity of modulation only leads to an incremental increase in capacity. So down at the bottom of this chart here, going from 2048 to 4096 QAM, it's a huge increase in complexity of signal, but it only adds 10%, less than 10% additional capacity. You go from 880 megabits per second to 960 megabits per second by adding so much more complexity to the modulation. Anyway, when I started with licensed microwave 15 years ago, QPSK and 16 QAM were really common modulations. Now 1024 and 2048 are pretty standard. The question is, why would you ever run slower than the peak modulation? The modulation you can support, and thus the data rate you can support on a point-to-point microwave link, depends on how much signal you can get across that link in a low noise licensed microwave environment. Lower received signal means that radios can't decode more complex information, so the bit rate goes down. The x-axis in my slide here is in decibels, which is a logarithmic scale, and I've assumed 0 interference because in licensed bands, the value of the license is your protection from interference from other users. The government gives you a particular piece of spectrum from one point to another and says nobody's going to interfere with you here. So I've assumed 0 interference. Anyway, you can see the capacity in megabits per second rise with the increase in available signal on the link. And that is solely due to the lower noise and more received signal supporting the higher modulation, getting you more bits per second. So it's possible to have some very complex information and some very high data rates across microwave links, but only if we have enough signal. It happens there are a few things that actively diminish or attenuate the signal that we need to get that speed. And these are free space path loss, rain loss, and oxygen loss. And these are the microwave killers. So free space path loss is how we describe the loss in signal on a point-to-point link due to the waves spreading out as they travel over a distance. They're not actually going away. They're just not all going in the same direction. They're kind of going off course a bit. They're spreading out. So note the x-axis along the bottom is doubling in distance for each tick on my chart. I just made this chart up. Also note there's a massive loss in signal over the first few meters for all of the bands, but it's much higher for the higher frequency bands. And this chart assumes no signal amplification, no antenna gain, and it is super abstract. You're looking at this and you're like, what the heck does this mean? So I made a little bit more of a practical slide showing, quantifying the effect of free space path loss on a standard microwave link. So let's talk in measurements we all as telco and ISP operators understand. Given a constant transmit power and a constant antenna gain, not size, but antenna gain, here's how a 960 megabit per second speed drops off due to the reduction of signal solely over distance due to free space path loss. And as you can see, lower frequencies with larger waves do better at longer distances. 5 gigahertz band doesn't even lose half of its capacity at 160 kilometers, while 80 gigahertz band loses all of its capacity at 40 kilometers. I've shamelessly lifted this chart off a talk I gave about satellite, which you may have seen at APNIC in Taichung or maybe OSNOG or NZNOG. Anyway, satellite is basically just space microwave with the occasional space laser. So all of the principles of wireless RF for satellite apply to microwave links. Heavy rain, higher band signal attenuation can be as much as 10 decibels per kilometer. And with decibels being a logarithmic scale, that means you can lose 90% of your signal in 1 kilometer at some bands in heavy rain. And again, this is a pretty abstract topic, so I made a slide with some real world numbers we can look at. Oops. Considering a fixed distance at which most of these frequencies still perform well, you know, we're not talking about free space path loss having an impact yet. 5 kilometer link, what happens when it rains? So it depends on the frequency. At 5 and 11 gigahertz, not a lot happens, but at 80 gigahertz, it gets ugly really fast. Even in medium rain, the 80 gigahertz band can stop working completely. 5Ks, medium rain, 80 gigahertz, stop working completely. Yikes, maybe that's why people aren't using it. Okay. So that said, rain is really complex. First off, it doesn't rain all the time. Second off, it's really very uncommon to see constant rain at the same rate over a long path. The illustration below shows what rain actually looks like as it falls, with small bursts here and there, not a blanket of constant rain across any single path or angle. Every path will be different. And you also have this idea that not every microwave service needs to work 100% of the time. Some people are happy with a service that works 99.9% of the time. Some people are okay with 99.7% of the time. Hence the idiom I use here in the title, YMMV, which stands for your mileage may vary. So oxygen, what? Oxygen, what are we talking about? Why is there an altitude scale on this chart? It turns out that some frequency bands perform really poorly just going through air. And because it's air, the higher your elevation, the less air you have, the lower the impact. So here's one case where some links should perform much better in Nepal and Bhutan than they do in Bangladesh. Sorry, Shaila. Anyway, this is, again, another abstract concept. And again, I have a real world speed chart to illustrate this. Here, Oxygen absorption is a linear function. The steps we see in my graph are due to my own distortion of the x-axis. I've tried to roughly double the distance of the x-axis with each tick. So remember, as elevation increases, oxygen decreases. So the use of higher frequencies at high elevations means less O2 absorption. But at sea level, essentially oxygen absorption and slightly above sea level, oxygen absorption limits the 80 gigahertz band to a maximum of 40 kilometers at most elevations. So you might say, where's the 60 gigahertz band here? It's not. My scale here starts at 2 kilometers. Oxygen absorption is so high at 60 gigahertz that links don't even perform at 2 Ks. Most 60 gigahertz links top out at around 1 kilometer. Major 60 gigahertz projects like Facebook's Telegraph network only stretch their links a few hundred meters at most. Oxygen absorption impacts propagation of radio waves depending on the frequency. So the low bands perform the best. Let's only use the low bands. We've ruled out 80 gigahertz. It's got rain fade. It's got oxygen absorption. Let's just use the low bands. Fair point, right? Here's that chart again. And one of the things that we see here is the best band from the perspective of free space path loss, rain fade, and oxygen attenuation doesn't even have the most licenses. There's even more channel capacity in the 5 gigahertz band, the best one for all of these properties, than there is in the 7 gigahertz band, and yet it's not the most popular. Why is that? The answer is regulation. Radio spectrum managers often set minimum distances for some bands and antenna requirements that map roughly to what I've cited in this slide. You want to use the fade-proof bands? You're going to need to be going 20 or 30 kilometers on your link, or the government won't let you do it. You can't use these bands to go across the street, where a 60 gigahertz link might work just fine. Why would a government make regulations like this? To ensure that users with requirements for really long links have access to the spectrum they need when they need it. Now, you might see on this chart, I've put some things called notional antenna sizes. What's up with that? Well, the government regulates antenna performance on these bands to make sure that there's good reuse of the spectrum. Small antennas might work for most paths, but as waves spread out, using small antennas can lead to congestion and exhaustion of spectrum. Why is this? Well, the smaller your antenna is, the less it concentrates the radio energy transmitting from it. Think of like a flashlight, and a laser beam and a flashlight, and kind of a big dish and the waves just spreading out and out and out. Anyway, the effect is directly proportional to the frequency in use. The chart below shows that at 80 gigahertz, you only need a 300 millimeter antenna to get a 1 degree beam width, but at 6 gigahertz, you'd need a 3 meter antenna to get the same concentration of waves. And so if you install a 6 gigahertz point-to-point link with a 1.2 meter antenna, you could be leaving a beam of interference 100 kilometers away at 5 kilometers wide. This sounds like a lot. It is actually a lot, but it is allowed by New Zealand regulations. What's not allowed in the 6 gigahertz band, though, is going any smaller on your antenna. Because if you used an antenna half the size, the beam width and interference path would be twice as big. Again, abstract concepts. Here, I've got some examples, but I cheated. I didn't make a chart. I just took a picture. So to get an idea about what these dish sizes mean, here's a microwave relay I built in 2009 using the 7 gigahertz frequency band. The dish on the left is 1.2 meters in diameter. The one on the right is 1.8 meters in diameter. And the guy on the ladder who's smaller than the big antenna is named Brian. Hi, Brian. So now we've discussed capacity, speed, band, attenuation, regulation, all really abstract terms. Let's get concrete about what people are doing with microwave in New Zealand, because I work in New Zealand. So that leads us to a conversation about how far microwave can go. And the answer to this very philosophical question is the Kiwi idiom, how long is a piece of string? Well, I mean, how long is a piece of string? I don't know. When designing a microwave link, your limits are spectrum availability, which we've seen, free space path loss, rain fade, oxygen attenuation, regulation, and whether you want your work to link 100% of the time, mainly based on rain fade, or maybe if 99.7% of the time is okay. So instead of asking how far can microwave go, it's more important to ask How far are telcos going with microwave? And this chart explains that. I've plotted the distance of more than 4,400 licensed microwave links in New Zealand. The box plots here illustrate the distance range that 50% of the microwave links fall into at a given frequency band, and the scatter plot shows the actual distribution in the outliers. I've eliminated a few data points from this plot to simplify things. Some links from a mountaintop out to some oil platforms that are actually well past 100 Ks. So talk to me later if you want the full data set. What do we see here? The longest links are at 5 gigahertz for sure. No question about that. Due to the small amount of radio spectrum available at 10 gigahertz, there are very few licensed links. Even though 11 and 13 gigahertz spectrum bands perform very similarly, there are a lot more links at 11 gigahertz band, mainly because of spectrum and equipment availability. There are a few long links at the 23 gigahertz band, and there are a few crazy long paths at the 80 gigahertz band. I've checked, and these long paths are backed up with other frequencies. Again, we'll talk about that more in a bit, but I don't think these links are engineered well. And as you can see, they're definitely outliers when it compared to the rest of the radio spectrum use in the country. So you might then ask, okay, this is where people have licensed their links. How far and how fast? Again, these are philosophical questions. If you want to build a 40 gigabit per second microwave link, you can do it. And you could take that capacity 30 kilometers from one high mountain to another high mountain, very little oxygen, if you only needed to use it when it wasn't raining or snowing. So what's better to do is to illustrate some common links that you'll see in the New Zealand environment as illustrated by that last slide. Lots of 7 gigahertz links operating at more than a gigabit per second and going up to around 70 Ks. There are 11 gigahertz links operating at more than 2 gigabits per second going 50 Ks. There are 18 gigahertz links operating at 2.6 gigs going up to 10 Ks. And there's 23 plus 80 and 2 plus 10. What's that about? It turns out some carriers are running 2 plus 10 gigabit microwave links up to a few kilometers long, sometimes using a pair of different frequency radios on a single dish at each end. That gives them a huge amount of capacity that's probably available 99.9% of the time, or 99% of the time. That's 10 gigabits per second almost all the time, with a lower capacity that's available the rest of the time when it's really raining hard out there. You say, well, that seems crazy and complex, right? It turns out it happens. It's not all that uncommon. Here are some examples of 10 gigabit microwave links in my hometown, Wellington, New Zealand. All of these have been installed in the last 2 years. Coincidentally, they're using an Italian brand of microwave equipment called CA. One thing I find interesting about these licenses is how the use of various frequency bands has changed over time. When I started with licensed microwave 15 years ago, we mainly used the 7, 13, and 23 gigahertz bands, but lately the most popular band in the industry has been 11 gigahertz. What's going on with that? In addition to the large amount of radio spectrum available at 11 gigs, a lot of the recent use at 11 gigs has been due to low-cost equipment options from Mimosa and Ubiquiti in the licensed 11 gigahertz band. Here's a picture of my friend Dale from Go Wireless, hi Dale, in New Zealand, putting together a Ubiquiti 11 gigahertz link in 2017. That brings us to a few words on equipment. Microwave equipment 15 years ago was mainly the big telco suppliers, Ericsson and Fujitsu, with an upstart called Aviat, an amalgamation of Digital Microwave Corporation and Harris Stratix, just entering the New Zealand market around 2006. Coincidentally, it's been around 14 years since I last lost my voice shouting at an equipment vendor. Italian manufacturer SIA and Chinese giant Huawei both entered the New Zealand market around 2010, and Ubiquiti entered in late 2017. You can see its trajectory will have it passing Ceragon and all smaller brands combined in popularity sometime in 2020. I bet that's already happened. As an example of some CA equipment, I took this photo on a mountain called Takarika in Havelock, New Zealand in January. The dish in the middle is the SIA 13 gigahertz link. And this wraps up the part of my talk on licensed microwave and equipment. Now for something a little bit different, a couple of words on ISM band linking. I can't actually say these things on a recording, so let's move on. ISM band spectrum is free to use and it's open access in most markets. It is very easy to follow rules that are often not followed. Users get no protection from interference, so it's difficult, but not impossible, to use ISM backhaul for cell sites or VoIP traffic. ISM band receivers require more signal than licensed radios to perform at a particular speed due to the presence of noise in their channel from other users, because anyone can use the spectrum. The 5 gigahertz ISM band is nearly equivalent to the 5 gigahertz licensed band in spectrum availability and transmit power, but almost nobody in the ISM band uses 1.8 meter antennas with it. So interference is the rule, not the exception. The 24 gigahertz band is just like the 23 gigahertz band, but it has around 3% of the spectrum availability, and ISM rules mean you only get 1% of the transmit power. Now, the 60 gigahertz band is just like the 80 gigahertz band, but with 10 or 20 decibels per kilometer of oxygen absorption and 10% of the transmit power. Oxygen absorption isn't a terrible thing if you want short links. It means that there's very little interference from other users, but working with 10% of the transmit power due to the ISM rules means it's hard to keep links going in heavy rainstorms. Another distinction between licensed microwave equipment and ISM band equipment is that ISM equipment nearly always uses a single channel for both transmit and receive, operating via time division duplexing, or TDD. TDD is more efficient for asymmetric traffic, which is great for home users who want more download traffic than they do upload traffic. TDD efficiency and latency are tied together, which is fine for short links, but it means that longer links are inefficient as the radios spend a lot of time waiting for the data to arrive. Talk, listen, talk, listen, talk, listen. As the distance gets longer, you have to wait longer to listen and wait longer to talk. TDD coordination is the idea that transmitters at a site might all transmit at the same time and listen at the same time, but that only happens in network with a single ISP. If you put two ISPs using different TDD equipment on the same tower, they can interfere with each other. TDD is also more efficient when there are larger packets, which require a longer time to transmit, which introduces latency. So if you want lower latency, you get more overhead and lower throughput. Finally, TDD equipment throughput claims always assume the highest latency and no interference, which isn't a realistic explanation for most serious telcos or ISPs. One example of wild throughput claims is Mimosa's B24. I took this photo and I have some experience with the B24 radio. The manufacturer claims 1.7 gigabits per second of throughput, but actually the best and most reliable use of the spectrum and equipment limits its throughput to less than 300 megabits per second. A lot of ISM equipment in 5, 24, and 60 gigahertz claims to be gigabit wireless, and sometimes it is. What you have to take into account is, as I said earlier, throughput claims assume the highest latency and no interference. Also, unlike with licensed microwave hardware or Ethernet switches, peak MAC rate is not peak throughput rate. This is because most low-cost gigabit wireless radios are just Linux routers, and they're constrained by their CPUs. If you remember Moinier's talk from Tuesday, you'll have some background on how that works. It means that gigabit rates might be achievable with large packets and low packet per second rates, but data rates fall into the hundreds of megabits per second with a standard IMIX, or traffic even tens of megabits per second if loaded entirely with small packets. This particular radio has an over-the-air MAC rate of 4.6 gigabits per second half duplex, but if you want to fill it with 64-byte packets, you get less than 20% of that capacity over the wire. So that said, don't take my warnings on ISM band radios as instructions not to use them. ISM bands are very inexpensive, the equipment's inexpensive, and I continue to use them for many applications. Here's a site I built in 2006 that's still operating today. The radio on it was replaced in 2017. It's running in the 5 gigahertz ISM band with very, very low power, a very small antenna, and a 3-kilometer path. And with that, I'll wrap my talk up. Okay, one picture of me to close the deck. Here I am attaching an antenna on a mast in Picton, New Zealand, also in 2006. This mast is also still around, and it has a pair of ISM band wireless links running on it today, just like the ones described in the last slide. I'm happy to take any questions now if there's any time left, and thank you. Thank you very much.
Thank you, John. I have to say I love the photos in the last two slides. We already have a couple of comments for you. First one is 80 gigahertz versus RANAID issues. What's your thought on that?
80 gigahertz versus
RANAID issues?
rain?
RANAID issues. Do you
Okay.
want
I can talk more about 80 gigahertz and rain fade. It is quite predictable, and it just, whether you use it for a service depends on how much availability you want and where you're using the link. If you're using the link in the desert, you may never have any issues using it. And if you're using it in a tropical environment like Manila, you may have problems with it in some months every single day. And you may need to combine that 80 gigahertz link with some other lower frequency microwave to make sure your service is going to work.
Okay, another question. Are there any regulatory impediments in New Zealand with regards to site access, pole access, or is it all based on commercial terms?
In New Zealand, it's mainly based on commercial terms, but there are environmental regulations that prevent you from building a large new radio mast on top of some mountains. Some parts of our landscape are sacred to the Maori people, the indigenous people of New Zealand, and we can't build on those. It wouldn't be right for us to do that. And also, some places people just don't want to see antennas on ridge lines. That said, we can usually build them down the hill from the top of the ridge so they're not seen from everywhere, or we can disguise them, we can color them, and so on. It matters more in cities, but no, it's generally very easy to install antennas anywhere in New Zealand.
Okay, last comment. Rain fade versus SNR versus throughput spectral efficiency over hertz.
Yeah.
Comment on that?
So what rain fade does is it decreases the amount of signal you have, and thus the signal to noise ratio. And when you have less signal, you have less, you can only get a less complex signal across it, so your modulation drops and your throughput drops. In the licensed bands, your signal to noise ratio is very predictable. Your noise rate is always going to be the thermal noise floor, background noise from the sun and the universe. But in unlicensed bands, ISM bands, you have other users to cope with, so it can be different everywhere.
Okay, I'm going to have to ask the last question to send an email to conference@apnic.net since we don't have time. Thank you so much, John. I am now giving back the mic to Sharla to introduce our next speaker. Over to you, Sharla.
Thank you. John, that was excellent presentation, very informative. And I would like to call our next speaker on the lineup, Mr. Tahir Hussain. He's working as a senior network engineer at Affinity, and he will be speaking on a prototype application for end-to-end path discovery on a CDN. Tahir, the floor is yours as we are a little bit behind schedule. Please take 27 minutes to finish your presentation. Please feel free to begin your presentation.
Thank you so much, Shaila. Just let me know, am I audible and is my screen shared? Hello, Shaila, am I audible?
Yes, we can hear you and we can see your presentation.
Perfect, that is great. Yep. All right, so I'll just begin. Okay, hi everyone. My name is Tahir Hussain, and the presentation that I'm going to be presenting today is a prototype application for end-to-end path discovery in a content delivery network. So my email address is tahir.bbs@gmail.com. So if you have any questions regarding my presentation, so we can have a discussion over it if you want to. So brief review about how I'm going to proceed is we're going to see how CDN architecture is. We're going to see a problem description and a problem that arises in a CDN architecture. Then we're going to see an aims and objective that we did for my whole application, a technical methodology that how I proceeded with the whole application, some discussions of the results, and some future work that can be done on this application. Right? Okay, so before diving in any more about my application or anything about CDN networks, I have to ask this question. Has your YouTube video ever buffered in recent times? All right, so keeping this question in your mind, we're gonna go and pursue the remaining of my presentation. All right, so YouTube videos. Even you can see that you can have a really less bandwidth internet connection, maybe a 2 Mbps connection or 3 Mbps connection. Your other things are gonna stuck or your other things are gonna lag, but your YouTube will never be lagging because of the technology that is running behind that. Even Netflix, Amazon Prime, you can see these streaming sites and you're gonna be witnessing that they don't lag anymore, or they don't provide you jitters with buffers. So why is that? So what is the technology that is running behind that? We're just gonna have a discussion over it. So the technology that runs at the heart of the CDN networks or at the heart of YouTube, Amazon Prime, Netflix, everything is CDN networks. And CDN stands for Content Delivery Networks. Right? So content delivery networks are basically networks that have servers, very powerful servers that are strategically distributed around the globe. And by the term globe, I literally mean around the globe. Right? So why is that important? So content delivery networks, they reliably and cheaply deliver your traffic. So that can be your video traffic, that can be your streaming traffic, that can be your audio traffic. So a lot of traffic. Even Facebook uses content delivery networks. That's why Facebook is so efficient and so quick. So how does it accomplish it that? So it accomplishes using distributed servers around the globe. Right? So there are two components, major components in a CDN network. First is the originating server, and the other one is the surrogating server. It's just like seeing or just like making replicas of the original content, but with all the copyrights, because everything is held by a single entity. So for example, if I upload a video at YouTube, let's say I am in Pakistan and I'm uploading a YouTube video somewhere and a YouTube server. So automatically YouTube is going to take that video and it is going to replicate that video across the whole globe. Right? So what are the benefits of that? So the benefits are optimal latency. So by the term optimal latency, I mean best user experience. Best user experience means that as soon as you're gonna just click on the video is gonna play up, the video is gonna pop up, right? So that is a good user experience. So this is a graphical representation of a CDN architecture or a CDN network. So if you can see that at the very heart, there is this originating server. So this originating server is the server that holds the actual content or that holds the original data. So all of my data, or the first time the video or any audio or any file is uploaded at this origin server, which is at the very heart. Automatically, as soon as the clients, you can see that there are clients at the different regions. There's a client in the Australian region, there's a client in the Indian Pacific region, there's a client in the American, North American, South American region. So automatically when they're trying to fetch this content, so instead of content directly being sent from the originating or from the heart of the server, it is replicated through their regional servers, and their regional servers or their surrogate servers, they tend to transfer the content directly to the users. So this reduces the latency and reduces the packet losses and stuff, and increases the user experience, enhances the user experience. So reports and trends. All right. So lately Cisco has said that nearly around 2/3 of the internet traffic is going to be videos and streaming and stuff. Netflix has alone reportedly over 1 billion hours of video streaming every month. So just imagine 1 billion hours of video streaming, which is approximately around 7200000 terabytes of video streaming. So there are more zeros that I have missed out, just have wrote this word. So a lot of data. So this is a massive amount of internet data that is going on. And since we are having 4K videos and HD videos and stuff like that, so high content data, and it has to be reliably delivered. So it has to follow a certain technology that enhances the user experience. Right. So problem in that. So the basic problem in the whole CDN network is that CDN itself follows, or it is based on BGP. So BGP is a very traditional and a reliable and a protocol that has been used for like decades. So it relies on BGP because BGP is the internet routing protocol. So the hard problem lies in BGP, which actually rides on the CDN network. So that is inefficient redirection. So we know that internet routing follows destination-based routing. So whatever my destination is, my packets are going to flow in that direction. And that is all based on BGP. So BGP follows that best path selection criteria. It has a long list of metrics. It has a long best path selection criteria. It follows that. But eventually what happens is, at times, what BGP thinks is best for us is actually not best for us. And this specific definition we call inefficient redirection. Let me go a little bit in detail and I'll let you know. So for example, as we know that BGP follows best path selection criteria, and the best path selection criteria, the heart of BGP is autonomous number systems. So autonomous number systems are routers or devices under similar administration. So I've just created a small, you can call it a diagram that says network 10. So this AS10 means a company, AS20 is another company or another ISP, AS30 is another autonomous number systems or another, you can call it entity, 10 is 50. Then I have AS10, 40, and 50. So this is my CDN server at the very left, and this is my origin server at the very right. So origin server is actually the server that holds the original content. CDN server is actually the server that is going to replicate this content. Now, since CDN network follows BGP at its very core, and BGP itself follows the best path selection criteria, which is on hop counts. So I can see that the content that is coming from the origin server towards my CDN server is always going to follow the below path, the path that I have shown here with the arrow. So the path is always going to be autonomous number 50, then autonomous number 40, and autonomous number 10, and then towards my CDN server, because that is the behavior of BGP. So the issue there is that, for example, there is a link congestion between autonomous number 40 and autonomous number 50. So if there is a link congestion here, automatically the content is going to deteriorate, or the content, the time taken from the origin server to replicate the content to the CDN server, that is going to reduce down because there's link congestion on the link, right? So although there is an other optimal path available, which is AS50, 30, 20, and 10, but BGP doesn't know that. BGP cannot shift the path unless this path is down completely. If there is link congestion on the path, there's always going to be issues on the path. So what I did, or what I came up with, is an application that can automatically be installed on the CDN server, or maybe on a Linux machine that is connected with the CDN server, and it can proactively monitor this path, or it can proactively monitor both the paths. And if it feels that there is link congestion on the below path, which is AS10, 40, and 50, it automatically shifts the path to the other path, which is AS10, 20, 30, and 50, which is the above path. So that since I have an other optional path, other backup path, why not to shift my content towards that path and then retrieve my content? And if the below links get stable, shift my content back again to this path. So this is a small application that I created, and I've linked that application with my autonomous number system 10, and then I automatically or proactively start monitoring my path. So the methodology that I've used in order to achieve this whole idea is Cisco's PPDI develop approach, which says to prepare, plan, design, implement, operate, and then optimize. So we're gonna dive into the steps that how I did the PPDI approach, and then we're gonna see what results came out. So first, preparing. So for preparing, I've used VMware Workstation so that I can simulate my whole idea inside a workstation, and I can easily work with that. For network emulation, I have used EVE-NG. So EVE-NG is a network emulator that you can use to depict your network as big as you want. So it depends on how you want to depict your network. My topology is made up of 5 nodes. So as I've shown here, see this has 5 nodes, 1, 2, 3, 4, and a 5. Exactly, I have used this in my test topology. For virtual machine integration or the Linux machine integration, I've used a Ubuntu 18.4 LTS, which is stable enough to be integrated with my whole topology. For programming language, I've used Bash. So Bash is the native language of Linux. So yes, I've used that of Ubuntu. So it's terminal programming language, and I've used that. for extracting and plotting the results that I can actually see that either my traffic is getting fetched via a congested part or whether a good path. So I've used smoke ping for that. So smoke ping is a utility that gives you very efficient results in terms of network congestion. Okay, so this is my methodology. So first I'm going to start, and this is the flow of my methodology, a very high level overview. I'm going to monitor, extract, compare, and then execute. So what I'm going to monitor? So monitor from here. So I'm just going to switch to my paints, and then I'm going to let you know that how I'm doing it. Okay. So here I am. So my Linux machine is integrated somewhere here. Okay. So this machine is going to proactively send out packets and is going to monitor this destination all the way from here. And it is going to keep on doing that, keep on going to the router 1, towards router 4, towards router 5, and towards this server. Because this has having an IP address of 5.5.5.5 that I've created on my EVNG environment. So I cannot, since we have a little bit constraint of time, I cannot show the whole the workflow of my application. I'm just going to tell you that how the application is working. So the originating server is having the IP address of 5.5.5.5, and it is advertised via this router R5 towards both the directions. Now, since BGP is also working on R1 as well, so it is taking the shortest path, which is from R1, R4, and R5. And the application is sitting here. The application is continuously monitoring this path. So if it finds packet losses or if it finds any deterioration inside this path, so what it's going to do is it is going to go inside BGP and it is going to tell that this path towards router R1 that this is not a good path, and it is going to add prepension into this path. So people who are familiar with BGP, so there's an attribute called BGP prepension, which I can use to tell the router that this path is not a good path and this path is a good path. So I can differentiate between two paths using BGP prepension attributes. So I'm going to say that this is a newly created path for you, and you're going to take this path in order if you want to fetch your content until this red path becomes sufficiently good. Okay. So this is the whole approach that I'm going to be using, which is my designing and my planning approach. Execution. So this is a detailed view of my that how my whole script, how my whole application is progressing. So it automatically takes. So first step is to probe the CDN using source IP from 01. So for basically it means that it is sourcing or it is trying to go and fetch the path attributes from the below links. So you can see that there's a cloud here, which is a net cloud, and there's R1. So it is taking the below with an E0, one size 0. So it is going to go from this path towards R4, towards R5, and towards the CDN server. And then it is going to check the path attributes. It is going to check packet losses and RTT. So RTT is round trip time. So it is going to take both the attributes into account, compare it with the above attributes. So it is also going to go from this interface E1/1, and it is going from R2, R3, R5, and it is going to check whether the above path is better than the below path. If the answer, so it says check the stats algorithm. If the answer is, let's say, yes, that the above path is better path, so it is going to execute a script, and that script is going to automatically go and telnet or SSH inside the router, and then it's going to change the route map that has the AS path prepension attribute, and automatically the traffic is going to be shifted from the non-virtual path or the deteriorated path towards the actual or the real path. Alright, so as soon as I implemented that, so I'm taking two attributes into account. So first attribute is the ping, and the other attribute is the trace route. So sorry, two utilities I'm using to gather out stats. So first I'm using pings. Now pings are used for the RTT and the packet losses, and also I'm using trace route so that I can verify that whether my ping results are accurate or not. So here you can see that these results are from a machine that is the Linux machine that I've installed. So as soon as I ping 5.5.5.5, which is my originating server, so you can see that I'm having packet losses. So at the moment, there is no congestion on the link, and I'm having 0 packet losses. And at the second line, I'm having RTT. So RTT here stands for round trip time. So RTT, minimum, average, max, and then I have the deviation. So I'm using the average time. So packet losses, so this 0% packet loss, this attribute, and then the average time, the average RTT time. Right. So I am going to extract out this parameter, which is a 0, and this slide, whatever the parameter at that point is, I'm going to extract that, and I'm going to extract the average RTT, which is the second one here. Also, I'm using my MTR or my trace route utilities to see what my path is flowing. So at the very bottom right, you can see that my trace route says that my packets are traveling from 192.168.18.150, which is this interface IP address of E1/0. Then it is going to 155.114.4, which is this interface IP address. So router R4's Ethernet 0/1. So IP address associated with that is 155.114.4. Then 14.4 is forwarding packet to 155.145.5, which is this router's IP address, R5 Ethernet 0/2. And then R5 is forwarding packet to 5.5.5.5, which is this IP address. So this is my packet flow, or my path that my whole topology is taking. So ping -c 10.5. So it is, since it is in the Linux utility, I'm not using regular Linux commands or the regular commands that are used. So it's just simple ping. So in Linux, if you want to grab or if you want to take any output of a command, you can just use a greater than sign, and all of that output is going to be sent into this whole file or this whole variable, whatever you want. So I'm pushing all of my output of ping 10.5 or 5.5 into this output. So this is the actual output. Which is 64 bytes from 5.5.5, and it's an ICMP core. So it is all going, so whole of this output, which is shown here in the black window, is put inside this ping-results output file. Then the next step is I'm going to take this file. So this is my whole file, and the objective of this file is to extract out this 0 and this average RTT time. So in the next part, what I'm doing is I'm taking this whole file, and I'm cutting and I'm chopping out this until I have the exact values that I can use to compare out. So you can see that in the first one, at the top right one, I am taking RTT. So you can see that RTT is a little bit bold. I'm grabbing this word. So grab RTT means that just find out RTT in this whole file and extract out that. In the next line, I'm taking RTT as my variable, and I'm delimiting the other factors. I'm getting the exact value of RTT. So here I can see that RTT value is 7.697, which is at the line 2. And at the here, I'm using this whole command, and these are set of instructions that are run, and I've got the 7.69 value. Similarly, I've done with the loss. So since at this moment, I don't have any loss, my loss is 0%. Alrighty. So once it has all the attributes, it is going to go into a comparison formula. So this is my comparison formula, that if loss, which we saw earlier, is greater than 7%, or equal to 7%, and round trip time is 20 milliseconds. So this is just a random value that I've chosen. Later on, we can revise these values as my network topology is. So if this value, or if any of these parameters are achieved, so greater than 7%, equal to 7%, or round trip time greater than 20%, automatically execute this script. So script is shifter R4 to R3, which means to shift to the optimal path, which is the above path that was a little bit longer, but it is optimal. And this is whole the script that is going to be executed. So it's a expect script. So expect script expects something from you. It is expecting the router's prompt from the output of the Linux machine. So as soon as the router's prompt is coming up, you can see that in my line number 4 here, which says set ES prepend 1111. So what happens is I am automatically adding path to my routes, and then I'm advertising to the direction of the traffic that is flowing towards router R4, which is the below route. Okay, so in order to depict my congestion and depict my deterioration path, what I've used a WAN emulator. So WAN emulators are devices that deteriorates path. So when R4 is sending traffic to R5, it is sending through the WAN emulator. Just to depict the congestion part, I've used this as my WAN emulator, or is a node to add the deterioration of the path. Alrighty, so once my application is done, so these are the test scenarios that I've used to gather out the results. So test number 1 is 0% packet loss, and the round trip time is less than 10 milliseconds. So these packet loss and round trip times, these values are set using the WAN emulator. So in the test number 1, I've used 0% packet losses, and I've used less than 10 milliseconds of round trip time. And this test has been run for 20 minutes. Similarly, test 2 is having 3% packet losses, less than 10 milliseconds of RTT, and still has 20 minutes. Test 3 is at 5% packet losses, less than 10 milliseconds, and for 20 minutes. Test 4 is 7%. Now this 7% is very important for me, because my scenario, if you can see that the condition that I've used is say that the loss is greater than 7% or loss equal to 7%. So as soon as my loss becomes equal to 7%, this script should trigger. So that is the whole objective. So test 4 is very important for me. So test 4 should trigger, and we can see that the path shifting towards the optimal path. So test 4 is basically the path which is following, or the lower path getting deteriorated and traffic shifting to the above path. Similarly, test number 5 has 4 parts, 5A, 5B, 5C, and 5D. So in 5A, I have 0% packet losses and I have 10 milliseconds. Then it is a linear increase in packet losses. So 3% packet loss, 5% packet loss, and then 7% packet loss. So in the test number 1, 2, and 3, since I'm having packet losses less than 7%, I'm seeing that there is no packet losses here. So you can see in the my traceroute utility as well. And this is an output of the smoke ping output. So at the bottom right, you have the smoke ping output. So the green part says that there is no packet losses. As long as the colors starts increasing and going towards red means the maximum number of packet losses. Then purple, then blue, then light blue, that means there are packet losses. Green means there are no packet losses. So in my test scenarios number 1, 2, and 3, I'm having no packet losses. Now the important part, test number 4. As soon as I'm having 7% packet losses, you can see that my packet losses are showing in the smoke ping. So the purple and the pinkish and the bluish. So you can see that these are packet losses depicting here. Also in the my traceroute utility, if you can see the nodes 155, 145.5, and 5.5.5.5, which is the second last and the last, you can see that there's 7.3% packet losses here. So there are packet losses. So as soon as this happened, automatically the script triggered, and this all happened automatically. And you can see that the purple line in the smoke ping, then it came to blue, and then it came to green because the path has been shifted. Also, you can see that in the nodes 3 and 4, you can see that the path is shifting from 45.50 towards 23.3 because it is shifted to the above part. And at the since I ran this test again, you can see that the path is shifted in the second my traceroute utility, which is says 12.2, 12.3, 35.5, and then 5.5.5. And now 5.5 is having no packet losses. So this is test number 5, which is linear test regression. And you can see that at the very beginning, it is this application linear testing has 0% packet losses, then 30%, 50%, and then 70%, 70% RTT, and then 7% packet losses. So you can see that in the smoking as well, I'm having first 0, which is green one. Then the packet losses increase a little bit higher because it increased till 3%, then 5%. And as soon as it got hit at 7%, you can see in the second smoking picture that the path is shifted to the the optimal path, and the whole the packet loss it just reduced down in the second picture again to the green ones. So the further work is I'm going to update my algorithm. So this algorithm is a kind of little static right now. So it can be based on AI, that it automatically takes the network congestion into play and then updates its algorithm. GUI for the application. Right now, the application is running barely on the Linux machines. So a GUI gives a good utility, a graph, and all the other scenarios. So that is also another part that can be done in the application. So integrating with artificial intelligence. So artificial intelligence is going to help me navigate me. It's going to help me understand my network furthermore, and it's going to update my algorithm as well. Also, you can see the technology that is running in this era is containerization. So containerization is that I just take all of my application, make it into a container, and then upload it that, so that any organization can just fetch that container, add their destination and source IP addresses, and then boom, the application would start working. Yep. All right, so a conclusion to my whole presentation is that the content delivery networks have helped reducing the buffering capacity. The project has successfully implemented a prototype application. So this is actually a working application, and this has been tested for quite a few of hours, like tons and tons of hours I've tested this application. So I cannot, since we have a constraint in time, I cannot just give the demo of the application, but yes, this has been tested pretty well. And it gives very satisfactory results as well. So I can see on my smoke pings that whenever the packet starts loss gets greater than the algorithm, 7% or whatever I've set, it automatically reduces down. So yes, it works fine. So these are some references that I've used. So these are some papers that I've analyzed. So there are papers on the internet about CDN networks. I've used those papers. I've used the Google Sheet workset, and then I've came up to this solution. So it is actually based on a real world scenario. So yeah, that was it from my side. I'm gonna just take control to Shogila. If you have any questions, so I'm more than welcome to answer them.
Thank you so much, Tahir. Great job on your presentation and also for wrapping up on time.
Thank you so much.
We are now open for questions. We can take 2 questions.
Yeah, sure.
I'm gonna check if there's anyone raising hand. It seems there's no questions to hear, so I am now closing the Q&A.
Sure. Yep. Thank you so much for inviting me. And yep, it was a great event so far. It's going great.
Okay, so thanks again, John and Tahir, for your excellent presentations, and also Sharla for moderating the session. I am now inviting you to participate in the poll survey, which should be popping up in your screens right now. Our next sessions are Women in ICT and a tutorial on home lab setup. So hope to see you guys in those sessions. Bye.